Have you ever wondered what's going on inside of a computer or your phone and what all of those chips do? Well, these things are collectively called integrated circuits or ICs, and they contain thousands of tiny digital electrical circuits. By digital we mean in binary form, which is something that works in one of two states, for example off or on, closed or open, 0 or 1. So how do we get from the idea of a binary state to integrated circuits? Let's start with some simple circuits. Here I've got a circuit that controls whether a lamp is on or off depending on whether a switch is open or closed. When the switch is open, the lamp is off, and when it's closed, the lamp is on. We can make this table a bit more concise by using symbols and binary states instead of words. So switch becomes S and lamp becomes L, with open and closed becoming 0 and 1 and on and off becoming 0 and 1. S and L are known as binary variables as they take on binary values. Now we can be even more concise and write the table as a Boolean Logic expression L equals S, meaning that L becomes whatever S is. So if, for example, S is 0, then so is L. Boolean expressions always have an answer which is either true or false. In itself, having a circuit produce an output the same as its input is reasonably useful, but what happens to be even more useful is a circuit which produces the opposite of its input. In other words, if the switch is open, the lamp is on, and if it's closed, it's off. It has the logic expression L equals not S. The second circuit has two switches, S1 and S2, connected in series. Starting with both switches open, which will take the value 0, let's see what happens for different open and closed states. With both switches open, the lamp is off. With S1 open and S2 closed, the lamp is off. And as you might expect, with S1 closed and S2 open, the lamp is off as well. Finally, with both switches closed, the lamp goes on. So in this circuit, the lamp will only be on when both S1 and S2 are closed. In other words, L equals 1 when S1 equals 1 and S2 equals 1. This can be abbreviated to the expression L equals S1 and S2. The third circuit has two switches connected in parallel, and as you might expect, the lamp comes on whenever S1 or S2 is closed, including when both are closed. So the table looks like this and can be abbreviated to L equals S1 or S2. Physically, these circuits are built using tiny transistors which act as binary switches, connected together to make logic gates. We'll not concern ourselves with how these gates are made, but it turns out that these basic logical functions of not, or, and and are all that you need to make any logic circuit. So let's look at how we might do this. First of all, rather than using words to describe logic gates, we can use symbols instead. Here is the NOT gate, which carries out the NOT function. It's got one input and one output, and if you recall, the output is the opposite of the input, as shown in the table. By the way, the formal name for this table when used in digital logic is a truth table. It's called a truth table because it shows all the possible outcomes for all input combinations. You can see that I'm using A for the input and F for the output. Here's the Boolean expression for the gate, F equals not A, which means exactly the same as the truth table. Let's look at the AND gate. This is its symbol and its truth table, which shows two inputs, A and B, and the output F. As we've seen before, we only get an output when all inputs are 1. The Boolean expression for this AND gate is F equals A and B. AND gates in general only produce an output of 1 if all of their inputs are 1. Here's the OR gate symbol, which is shown with two inputs and one output. As its truth table shows, you get an output if either of its inputs are 1. Its Boolean expression is F equals A or B. OR gates only produce an output of 1 if any of their inputs are 1. It's worth mentioning that AND and OR gates are not restricted to two inputs. Here's an example of them having 3 inputs. The logic is still the same though. For the OR gate, if any of the 3 inputs are 1, there'll be an output. And for the AND gate, there'll only be an output if all 3 inputs are 1. Typically though, you won't go above 5 inputs, and of course, you'll only ever have one output. Logic gates only become useful when they are combined together to make logic circuits that solve a particular problem. For instance, this circuit is designed to add together two binary values. So, how do you design a logic circuit? Well, first you start with a problem, so let's make one up. Let's say that I want to design a simple car alarm system. It's going to set off a siren if any of the doors are opened or if the car is physically knocked by someone. We'll need some sensors, a car door open sensor and a vibration sensor, and an arm disarm switch, as we don't want the alarm to go off when we're just getting into and out of the car. All of the doors are connected to the door open sensor. We don't care which one is opened, just that one is. So we have two input sensors, let's call them D for door and V for vibration, and an arm disarm switch A and a siren S as an output. The first step is to decide what we want to happen for each combination of the arm, door and vibration inputs, and we do this using a truth table. Inputs go on the left side of the table and outputs on the right, so the columns are arm disarm A, door D and vibration V on the left and siren S on the right. The next question is how many rows are needed to be able to cover every combination. Well, since each input can take two values, which are 0 or 1, and there are 3 inputs, then we need 2 times 2 times 2 or 8 rows. We now complete the input side of the table by putting in each possible value starting with all zeros. Here's where you need to be able to count from 0 to 7 in binary, as it's far easier to fill in the table that way. So the next row is 0, 0, 1, which is binary 1, and then 0, 1, 0, binary 2, and so on up to 1, 1, 1, which is binary 7. Okay, now we've got all the inputs filled in, it's time to look at the corresponding output. We could, and generally should, go through each line of the truth table in turn and ask ourselves what should happen to the output for that combination of inputs. In this problem though, we can group together the cases where the arm switch is disarmed. We definitely don't want the siren to go off when the system is disarmed, irrespective of whether the doors are opened or closed or whether we detect a vibration. So the output for all of these cases is that the siren should be off, or 0. That's the first 4 rows in the table. We're now left with what happens when the alarm is armed. Taking each in turn, if the doors are closed and there's no vibration, the siren should be off, so it's 0. If the doors are closed and there is a vibration, then sound the alarm, so it's a 1. If a door is open and there's no vibration, then sound the alarm. Finally, if a door is open and there is vibration, then sound the alarm. To change the truth table into logic gates, we first convert the table into a Boolean expression and then use this expression to design the circuit. The easiest way to change from a table to a Boolean expression is to write down the cases where the output is 1 and then collect them together as OR cases. They're OR cases because we get an output if any of those conditions are true. So for each case in turn we get A and not D and V, A and D and not V, A and D and V. And putting these together as one final expression, we have S equals all of these individual expressions OR together. To change this expression into a logic circuit, we first start by drawing the inputs A, D and V. At this point we don't care what sensor is actually connected to these inputs, as we treat in the logic part as a black box. We then take each part of the full expression in turn. The order doesn't matter, but working from left to right is the conventional way of doing it. So first we look at A and not D and V. A is ANDed with a not D and a V. So we need a 3 input AND gate and a NOT gate. D is connected to the NOT gate and then its output along with the connections from A and V are the inputs to the AND gate. The next part of the expression is A and D and not V, which now extends the circuit to this, new parts under the last part. You can see that I've added a new wire to V and connected it to a NOT gate and to give the not V part of the expression. A is the same as before, so we already have a connection. D currently goes through a NOT gate, so we need a connection that doesn't. These 3 new inputs are ANDed together. As we've now got 2 expressions, the output of each needs to be ORed together as shown. Finally, we add the remaining gates for the last expression A and D and V as shown at the bottom. This one is just straight connections into an AND gate, which is then connected to the OR gate. This completes our circuit. Let's test the circuit by running through the original truth table. I've added some information to show the binary values at different points in the circuit. As before, we start at 0, 0, 0 for the input and look at the output. In this run through, if we have dark green wires, that means off or 0, and the light green wire means on or 1. So 0, 0, 0 gives 0 output as required. I'll step through the others quickly. 0, 0, 1 output 0, 0, 1, 0 output 0, 0, 1, 1 output 0, 1, 0, 0 output 0, 1, 0, 1 outputs 1, 1, 1, 0 outputs 1, and 1, 1, 1 gives 1. So our circuit is the same as our truth table, which means we now have a logic circuit for our car alarm. Whilst this isn't a particularly complicated circuit, it is more complicated than it need be, and it can be simplified. There are a couple of formal ways of doing this through the use of Boolean laws and a technique called corner maps, but these are a bit too advanced for the moment. We can, however, simplify the circuit by looking for patterns in the truth table. In the case of the car alarm table, we can see that if we just think about the D and V inputs when the output is 1, that they look like an OR gate. Indeed, when we framed the problem in words, we said that we want the siren to sound if the door's OR vibration sensors were triggered and the alarm was armed. So a much simpler expression seems to be S equals A and D or V, which gives this circuit. There's also another possible expression from the truth table that gives the same result. S equals A and V or A and D. We can only really arrive at this one using Boolean laws. Now these three circuits are equivalent to each other and all are equally correct, but as a rule the simpler circuits are easy to build and so we should aim to keep it simple. Finally, it's worth looking at the reverse process where you have a circuit diagram and you want to figure out what it does. Here's a different circuit to the car alarm one as an example. To reverse engineer this, we simply write out the logic expression which is present after each gate, starting from the inputs and moving toward the output. So starting with input A, we write not A after the not gate. For the OR gate, the expression is given from the top input, which is not A, and the bottom, which is B. So the expression is not A or B. For the input C, the AND gate expression is B and C. Finally, the last gate is an AND of its two inputs, which is the output of the previous OR and the output of the previous AND gate. So the final result is Z equals not A or B and B and C. We can now put this into a truth table. With 3 inputs, there are 8 combinations. There are 4 gates in the circuit, and given that we want to record the state after each, we add those columns to the table, the last one being the output of course. So the intermediate columns correspond to the output at each gate, for instance not A or B, and so on. Now we go through each combination of inputs and write down the state after each gate in turn. Starting with 0, 0, 0, we get 1 after the NOT gate. Moving down each combination, these will all be 1 for the output and these will all be 0, since not 1 is 0 of course. Next we move to the not A or B expression, which is what you get after the OR gate. Remember, we're ORing the NOT gate output with the B input here. So 1 ORed with 0 is 1, and again 1 OR 1 is 1, and so on. The B and C expression uses the 2 B and C inputs, so we get 0 and 0, which is 0, 0 and 1, which is 0, and so on. Finally, the output Z ANDs the values in the not A or B column with the values from B and C column. So we get 1 and 0, which is 0, and again the same for the next 2 rows. Then 1 ANDed with 1, which is 1, and so on. So that's the final truth table, and it shows that we get an output when A is 1 and B and C is 0, and when A is 1 and B and C are 1. Now the eagle-eyed amongst you will notice that the output Z is exactly the same as the B and C column, which means that the circuit can be simplified to Z equals B and C. In fact, the input A is irrelevant to this circuit as its state doesn't affect the result. So the circuit turns out to be a simple AND gate with inputs B and C. We've now seen how to reverse engineer a circuit and visualize how it works from just its truth table. Well, there we have it, an introduction to Boolean logic and digital circuits. We've looked at how the idea of digital switches leads us to logic gates and learned how we can combine these gates to make useful circuits. We've only just scratched the surface of digital and Boolean logic, so do check out my other more advanced videos when they're available.